initializing. All right, so what we have here is midterm review for 2016 for calculus. And we're going to start with the related rate. Water fills a cone at 3 cubic meters per hour. What's the rate of change of the radius when the height is 1 meter? And I give you a little cone down here with a radius of 3 and a height of 2 meters overall. You know this is a related rate because it has something for time. And I would ask you for the knowns. Well, the knowns are this. dV/dt is 3 cubic meters per hour. You guys agree? I would ask you for the unknown. What's the rate of change of the radius? I think you're looking for dr/dt. At when the height was 1. So I suppose I could put a line here, put the height equals 1 meter when h was 1. I probably would give you the formula if I gave you a cone. I doubt it. All right. We all know that. Probably not. So there's the volume of a cone, right? 1/3 pi r squared h. All right. Now, related rate, you don't have to get to one variable, but we'd like to often. And we sit here and say, oh, I see that the formula has v in it and r and h, 3 variables. All 3 are changing, right? As you fill this tank, all 3 of those variables are changing. Because as the water level goes up, you know, there's r, and now it's higher, and the r is bigger and the h is bigger, right? Everything is changing. So what we're going to do is find a relationship, all right, between r and h. And that relationship this time, if we see is 3:2, this is completely out of scale, right? We know that's r to h at any given point. And we have similar triangles. Often there are similar triangles in related rates. Often there are related similar triangles in optimization. So I get 3/2 equals r over h. Cross multiply, and I get 3h is equivalent to 2r. And since I want dr/dt, I'm going to want to get rid of h. So I'm going to solve for h. H is 2/3 of the radius. How exciting, because now I can take my formula along with this whole relationship and write the volume is 1/3 pi r squared. Instead of h, I could put in 2/3 r. And with some quick and handy little mathematics, we put on our freshman algebra hat, and we get that volume in this case for this particular right circular cone is 2/9 pi r cubed. And we should be thinking, that is awesome, Mr. Anderson, because now I can do implicit differentiation with respect to time. The derivative of v is dV/dt with respect to time. Derivative of 2/9 and pi are both 0, so I don't do it. I do 2/9 pi. Derivative of 3r cubed is 3r squared dr/dt. I'm sorry, I said 3r cubed. I meant r cubed is 3r squared. We can do a little reduction or a little simplifying here and get dV/dt equals 2/3 pi r squared dr/dt. Now, at this point, someone in the class is going to be saying, well, Mr. Anderson, I know dV/dt. I know I want dr/dt, but I don't know r. I only know h. Do not freak out, because you do know, if you know h, you can figure out r, right? So I'll come back here and figure out r first, all right? Because I think it's still faster to do it this way. So so 3/2 h is equal to r. You guys see it? And if h is 1, r is 3/2 times 1. So r is 3/2. So now it's plug and chug. Here we go. 3 cubic meters per hour, equals 2/3 times 2/3 pi times 3/2 squared dr/dt. And I see that I get, when I do some math here, I get 3 meters cubed per hour equals 2/3 times 9/4 is, well, 3/2 is going to cancel one of them. So it's 3/2 pi squared dr dt. So divide both sides, 3 divided by 3/2 pi. I think I get 2 over pi meters per hour. And this is pretty standard affair, dr dt. And that makes sense to me, because if the tank is filling, the rate of change of the radius should be positive, right? And since there's pi in the original formula, it's not surprising at all that there's pi in the rate of change, right, guys? Way back here, since there was pi in our original. And unless I made a glorious math mistake along the way, I'm sure that's the answer. All right. Again, related rates. I could do it on a. I would probably do either a cube or a right, or like a right rectangular prism, something like that. Something a little easier. This has more variables in it. All right. We're getting to a point soon where we'll start seeing these on testing quizzes, but for the midterm, I would expect something else. All right. Implicit differentiation. You should immediately look at this and know, hey, I can't solve for y because y is in sign, right? You can't do it. You just can't. You can't get y equals on this sucker, all right? So what we're going to do if we're going to find dy dx is do implicit differentiation. I will go through the step of dx dy today, but we should be just doing y primes. So I take the derivative of 3x squared, and that should be 6x. I'm going to write a really small dx here, all right, if you're going to do it that way, but minus the derivative of sine y. Derivative of sine is cosine y. And then it would be, and again, I'll write it really small as a dy, but really, all right, we're going to deal with those, all right. And the last step is on the other side, derivative of cosine is negative sine x, and again, with respect to dx. Everybody, if I divide everything by dx right now in black, I want you to see that anything you took a derivative with respect to x, the dx is canceled. And anything you took a derivative with respect to y, when you take dy divided by dx, you get y prime. So often as we practice this, we want to get to the point where we're actually just writing this line and skipping this line. All right? I took the derivative of 3x squared with respect to x and got 6x, and I don't write dx then. I just write 6x. I took the derivative of negative sine y and got negative cosine y. Boom, y prime. No chain rules buried in here, okay? And then equals, and then the last one with respect to x. So now you just got to solve for y prime. So I'll send 6x back into the other side. Now, I do that first, and I see everything is negative. So I make everything positive, right? All 3 terms are negative when I moved it. You don't have to. It's just prettier. Then I divide. So your 2 options are 6x plus sine x over positive cosine y, or you could have negative 6x minus sine x over negative cos y. But listen, I guarantee on the AP, the multiple choice one would be all the positives. And we found dy dx. This is on the midterm, something like this. All right. Could have a chain rule mixed in. If you want to see that, we could do. I could make up one pretty fast. If I did 3x squared y minus sine squared 3x equals 4y. Again, now this time I'm not going to do. This time I'm not going to do dx and dy. I'm just going to do y prime. So I look at the first term, 3x squared y, and you should say to yourself, oh, that's going to be 2 derivatives. Yep, and for one was 6xy. When you take the derivative with respect to x, you get 6xy, and we divide by dx immediately in our head, and it's gone. The other one it creates is when you take a derivative with respect to y. And when you take the derivative with respect to y, you get 1 times 3x squared is 3x squared y prime. product rule, right, guys? X and Y, both in the same term. Product rule. F derivative of F and G is F prime G plus G prime F. You bet. So when you looked at this term first time, you need to see that there's two functions here, F and G. Okay. When you take the derivative with respect to X, right, you do just this portion, which leads you to here. All right. Then you do the, now if I call the first term F, G, right, F prime G, then you got to do G prime. What's the derivative of Y with respect to Y? 1 Y prime times 3x squared. All right, so it's two terms. And again, there's a lot of opportunity to look over a problem like this. You might, using your answer book and the odds to do some review. The next one is minus, a whole bunch of chain rule crap here. Here we go. Minus, bring down the power, 2 sine 3x. What's the derivative of sine? Cosine 3x times, what's the derivative of 3x? 3. And there's my beautiful dead spot on my board. All right. Now, this would also be dx, right? But I am dividing immediately by dx. So I just have that blue term. Equals, then the derivative of 4y, which is 4y prime. The derivative of y is 1. So this is 4y prime. I have to get the y prime. Now this is algebra. This is algebra 2. Got to get the y primes on one side, everything else on the other. I see a y prime here and here. So I'll send 3x squared y prime to the other side and get 6xy minus 2 sine 3x. Cosine, well, hang on, cosine 3x times 3. Can I change the 2 to just 6 here, everybody? Is that okay? Because 2 times 3 in the blue term is 6. All over, well, okay, so hang on, I'll write it. 4 y prime minus 3x squared y prime. This is my favorite trick. I can do this right now, factor out the y prime, and now I just got to divide it. If I divide it, I'll write y prime equals dy dx equals the stuff on top, and I can never change the argument, guys. I can't think to myself about, the only thing I could factor out of the top would be the 6. I can never get at the 3 in the arguments. Over 4 minus 3x squared, but there's nothing at the bottom to factor either. Everybody, there's the derivative of that red curve, all right? It's not a function, it's a red curve. And that's y prime. Okay, no second derivatives tomorrow on this. We're going to get there. Pretty soon, next quarter, we're going to start taking the derivative of this, right? Because we're going to want to graph that red curve, which means we'll need to know concavity eventually. We'll get there. We're going to stick to review today. That is the answer for that problem. All right, we'll keep rolling.
Mr. Anderson?
Yes.
So I know you said that you split the test for me in 2 parts, but like, when are you guys taking the test so I know not to call you guys? Because I don't want to sit here and watch you guys take the test.
Oh, you don't have to call us.
So like, what day is that? Like tomorrow or Thursday? Or
Just Thursday.
but we're not. But do you guys have 8 hours tomorrow?
No 8 hours tomorrow.
So I don't call you.
You don't come up. You don't call me tomorrow or Thursday or Friday. Well, you can call Friday. I'll be here, but there's no one else is around.
Okay.
Okay. All right. Here's the one I think you guys don't like. Sketch, and I only went with a few conditions to keep it short. All right, and this is again out of some chapter 4 stuff because we've been doing 4, 5, and this was in chapter 3 also. Okay. I said sketch a function that has f of 0 equals 3, f prime of 1 is 0, f prime of x is less than 0 from 1 to infinity, and f prime of x is greater than 0 from negative infinity to 1. And I want it to be f prime prime to be less than 0. All right, let's be clear. This is pretty easy. 1, 2, 3, let's make sure we get credit for that one. Everything else you have to know. All right? So I take care of the one easy thing. I know that I want to think about this. When f prime is less than 0, this function is decreasing, right? And when f prime of x is greater than 0, it is increasing. So from 1 to infinity, this thing is going down. So I'm picturing in my head some sort of curve like this. Huh? Yeah. It could be steeper, it could be shallower. I mean, it could be this way. That's still decreasing, right? It's just how fast the rate of change if it's both negative slopes. I'm just thinking that. I just draw it that way. And the increasing from negative infinity to 1 looks like that in my head. And I'm just using that in my head, right? Increasing and decreasing. Increasing from negative infinity to 1 and decreasing. At 1, I'm looking for a critical point. Right? And since it's going from increasing to decreasing, what do we know about this? It's going to be a local max for sure. It's actually a global max in this case because of the way it's written. But it's a local max. And finally, what does f prime prime less than 0 mean? It means that the concavity is concave down, CD. Concave downward. So I'm picturing these black lines, okay, but I'm going to get rid of them. And I'm going to draw a curve now. And the first thing I'm going to do is I'm going to say, hey, well, I guess it has to be, I know that this point has to be above here because it increases all the way. So I would just draw a parabola personally. It goes through there. Mr. Anderson cheat, right? Make the point bigger. That actually passes through. I would not make this, I would not change the, I wouldn't have any infinite or discontinuities of any sort in it personally. Any jumps, or you could, but why bother? And everybody, this function meets those conditions. Alright? Likewise, we should be able to look at a curve and go back through and define sections, alright? So if I draw a curve, alright, everybody, I can define sections of this curve too, just looking at A, B, C, D, and L. What I didn't call out, and I'm going to go to a single page here, what I didn't call out, and I can do those letters in different colors, I didn't call out W or V or capital U. I should make these capital letters more obvious. I didn't call out these 3 points. I didn't call out the x-intercepts or the y-intercept, did I? I could, but that would have been pre-calculus days. What I called out here were points so we could define increasing, decreasing, points of inflection, and concavity. We should be able to define, when we look at this graph, all the increasing sections. Right? And immediately know that if I want the increasing sections, we're going to know that f prime of x, if I call this function f of x, is going to be greater than 0. Right? And sometimes students get thrown by this arrow, right? But it is increasing here right now, okay, guys? All the way up. So I think it increases from negative infinity to A. Where else? C to L. And that's it, isn't it? And that means it's decreasing everywhere else. That means it's f prime of x is less than 0. From A to C. And from L to positive infinity. And again, this time we're just going the other way. We're looking at a curve and defining it, okay? Versus me telling you those sections. The other thing we should be able to do is define concave up and concave down. Alright, starting from the left, I see it's concave down from negative infinity to B. Alright? And then I see it's concave down from D to positive infinity. Again, guys, this will take some practice using the suggested problems or your textbook, okay? I would imagine you're feeling a little secure about this, but might not be able to. The only place it's concave up, I think, is B to D. All right? And we should be able to see from the graph, hopefully I can remove these red curves, we should be able to pick out the critical points and the points of inflection, where the x values occurred, not the points of inflection. The x values of the critical points and the x values of the points of inflection. That would be the last thing we'd really pull out of this graph. And we should be able to find the local max and mins, but I think you see A, C, and L are the local max and mins. We're not going to go there today. But I think the ones that get us is where are the critical points? Where is f prime x equals 0? How about at A, C, and L, right? And then where are the points of inflection? B and D. Points of inflection happen at x equals B and x equals D. And you notice I didn't say that f prime x equals 0. You notice I didn't say that f prime x equals 0. It probably does. But what defines the point of inflection is a change in concavity, negative to positive here, right? And in this case, since it's a polynomial, f prime x, the second derivative of x, f would, the second derivative of f would be 0. All right? And again, that's working the other way. I won't put a problem like this on the midterm. What I will put on the midterm is a condition problem and have you draw me a curve, all right?
So the point of inflection is like the middle part where it's going down or up?
It's when it changes from down to up. You notice how here it's negative, how the tangent line of the blue curve here is above? And when you... Alright, middle point. You gotta be careful because I can draw it a different way. That's a point of inflection too. On the red curve I just sketched the bottom.
Okay.
Right? Whoops.
Right.
Because it can be, whoa, all kinds of problems. Why was it doing that? Alright. It can be right there, right? So that's point of inflection too. X cubed is one of those classic ones. But again, those are the things, again, that would be newer stuff. You guys agree? That has not been on a test. It will be on the midterm. Yes. Optimization, one simple optimization problem will be on there of some sort. It will not be hard because we haven't done them. We should be able to do a fenced area or something like that. Everybody, I want to do one of these. I will tell you that if I give you a root function like this, I can figure out the domain. You should automatically know this is a root function. We should see that the domain of this root function is what? Negative half to positive infinity. I can ask all that. I can ask for the derivative tomorrow of this. What I won't ask tomorrow or Thursday is this. That's the end. We're going to do all those parts. I could ask for the graph of this function, right? That would all be legal. And you might say, oh yeah, I remember square root of x, right? So I'll factor out the 2. And so I know that this is going to be back half. So if there's negative 1, it'll be back a half. And the 2 underneath basically stretches it a little bit. So there is the function f of x. You want to graph it. Now, we know that this is a one-to-one function. Passes the vertical line test to be a function. Passes the horizontal line test. Alright? So we know we can find the inverse. The thing tomorrow that makes this one a little difficult is you got to use the chain rule to get the derivative. And we don't want to leave it as a radical to do that. What we want to do there is think of the function in terms of an exponent. And I always think positive half, right? And this should be simply automatic, and it will say do not simplify. 1/2, 2x plus 1, reduce half by half, which is negative half, times the derivative of the inside, which is just 2. Now, if we were going to graph this, we'd have to simplify. You guys agree? Take 2 times a half, get rid of it, it's 1 over the square root of 2x plus 1.
Wait, we can do that simplification. Right?
Yeah.
2x plus 1.
Yeah, so if you run, I'll take both answers. Yeah, so it goes there. All right. Now, backing up, so we kind of keep thinking about our pre-calculus. We're moving, just so you know where we're going. We have finished chapter 4, all right, with antiderivatives. We skipped Newton's method, we got to come back to it. We're jumping to chapter 7, then jumping back to 5 and 6, and that's the end of the year. All right. In 7, we got to find the inverses. And we remember that a function is simply a machine that takes x, you input x, it gives you y. The inverse, you input y, it gives you x. So I have to solve this function for x. Square both sides first, in this case. Divide everything by 2. And looky, looky, what do I got? I got x is equivalent to 1/2 y squared minus 1/2. All right? And I know then that this has got to be my inverse, but we don't do functions in terms of y. We always do functions in terms of x, so we switch the variable, just like it's mirrored across the y equals x line. And I also know that it's not a parabola, even though that's a parabola. So I have to put a domain on this. So I go back to my original function graph up here, and I look at it and say, well, I'm not interested in the domain of it, I'm interested in the range. So y is an element of 0 to infinity. So my original function here in the red, I know that the y will become the x. So the element for the inverse has got to be 0 to infinity. That won't be on there tomorrow. This is pre-calculus. This is not calculus. All right? This is 7.1 in our textbook. To give you a reminder. The actual truth is we're going to want to take the derivative. We're going to want to know the rate of change of the inverse, which is obviously substantially different than the rate of change of the original function. And there are some shortcuts we're going to prove with that, all right? But we have to be comfortable finding the inverse, all right? Tomorrow, you have to be able to do the chain rules. Woo, I'm flying. I know it. I'm moving fast. Let's keep rolling. Oops. You want to do an optimization? So what if I told you I want to do an optimization problem? I'm going to use the textbook. Oh, we should do one anti. I can't remember. You probably want it to be. We learned a rule about doing the antiderivative, right? We know that if this is order 3 for the first term and order 1 for the second term, the antiderivative is going to have to be one higher, order 4 and order 2. So if we simply add 1 to those orders and divide by the new power, and we always get what? Plus C for calculus. You can't leave it like that. So you'd have to take 1 second and write this. And how do you know you're right? Guys, you should be machines at taking derivatives now. What's the derivative of 1/8 x to the 4th? 1/2 x cubed. What's the derivative of negative 3/2 x squared? Negative 3x. And what's always the derivative of c? 0. Alright? So, again, antiderivatives. And again, it comes down to we've learned this rule. And you won't have to do the rule for this test, okay? Alright? That's the rule we have learned. when we integrate x to the n, we get x to the n plus 1 divided by the coefficient n plus 1, whole plus some constant.
Excuse me for the following announcement, but we will be having a menu change on Wednesday. Instead of chicken sandwich.
Alright. Maybe the last one, maybe I'll record one curve sketching after the bell rings, but we'll do this one in class, and then I can do one curve sketching. And again, there will be curve sketching on the final. Find two numbers whose difference is 100, and product is a minimum. I mean, I want the product of x and y to be as small as possible. Well, okay, well, two numbers. First thing, there's no real picture here, okay? But how do you write a difference? Something minus something. Do we know either of the two numbers? What do you want to call them today? X and Y. I'm with, here we go. I can't believe Anthony is on a roll today. Here we go, X and Y. So X minus Y equals 100. You guys agree that's a difference? Awesome. How do I write a product? All right, I'm going to call it P for product, so it doesn't get confusing. Everybody, you should be very excited because we have enough now. Because what do I want to optimize? The product, P. Go you. But the problem is when I look at my beautiful equation for product,
You have P.
I have P, but what's on the right side?
You can use the other one.
I can use the other one because I got to get the one variable here to optimize the product. So how about we move Y? You guys agree with that obvious choice?
Yeah.
So the product is equal to X times 100 plus, wait a minute, holy crap, math mistake, Y times 100 plus Y, you guys agree? I just replaced X, and I moved the Y on the other side. All right. How about I distribute it, because I'm going to have to take a derivative here, and I don't want to do a product rule. I'd rather distribute and take the derivative of two terms. You guys agree? All right. I want to optimize P, so let's find P prime. I think it's 100 plus 2Y. You guys agree? Set equal to 0 because you want to. Now, if it's going to be a minimum, we all know the first derivative rule. All right, I'm sure we all do. First derivative says if you want a minimum, it's going from negative to positive. All right. So I set that equal to 0. And does everybody see that the answer for y is negative 50? I'm not going to go through y. It's just negative 50. All right. To find two numbers, so I go back up to my original equation. And the two numbers should be, if I plug in negative 50 for y, do you guys agree I get positive 50 for x? So the two numbers are 50 and negative 50. What's their product? Negative 2,500. That's the minimum, right? Because it's the biggest negative number you can create. If you want to prove it, think about what makes this. It's going from to be a minimum, it's going from negative to positive, right? So you think of a number to the left of negative 50. How about negative 1 million? Negative 1 million times 2 is negative. You think of a number to the right of negative 50. How about 0? 100 plus 2 times 0 is 100. That's positive. Negative to positive. First derivative rule can justify that solution.
That would be on the final.
Sure. I'm sure it's something easy. I haven't looked at it. I'm going to copy it from last year. This is an easy one. Again, setting it up. Again, the other easy one would be a fence project, right?
Yeah.
A fence in a river. We just got introduced to, but these are all in the textbook too, guys. Take a look at the odds in the textbook. The other one that will be on there will be something like, and I'll look in the book, like 4 or 5, section 4.5 in our textbook. Number, yeah, you could do like number 8 or number 2. Number 8's good. I'll do 8. You can look up odds like this. I would probably put this something like this because this is a good example. Again, I'd say no calculator. You can't use your graph calculator. And I'd ask you for the first and second derivatives, which are gimmies. I'd ask you for the critical points. What you get from the first derivative, I'd ask you for when is the second derivative 0. Then I would ask you to find increasing, decreasing, concave up, concave down. And finally, I'd ask you to make a graph of this from those points. Find those local max and mins, okay? everybody, what I'll do is I'll pause this because the bell's going to ring, and I will take 4 minutes to do all of that, which if you think about it is an absolute dog sprint. And I will post this on YouTube and send you guys the link.
Thank you.
Test is Thursday. So we want to find and sketch this curve. So if we're going to do that, we're going to find the first derivative first, which is this, which I will factor, pulling out the 60, not the 60, the 15x squared, that's common, which leaves positive 4 minus x squared. So plus or minus 2 and 0 are the critical points. This makes 0, plus or minus 2 makes that 0. So 3 critical points on this problem are 0, plus or minus 2. Then I'm going to find the second derivative from here, and I'm going to get 120x minus 60x cubed, and again 60x is common, so pull that out to get 2 minus x squared, and what makes y prime 0 is x equals 0 and plus or minus the square root of 2. So from the standpoint of defining our points, we have the critical points of 0 plus or minus 2, and we have the second derivative at plus or minus the square root of 2. I would ask for all that information usually. Then I would say, where is it increasing and decreasing? So we're going to have a sign table for this. Alright, and I'm going to have negative 2, negative square root of 2, 0, positive square root of 2 is 2. I'm going to have f of x, f prime of x, f prime of x. And I'm going to leave myself some notes. Alright, when I plug in 0, I can tell that 0 is also the y-intercept when I go to the original function up here. Plug in 0, you get 0. Square root of 2 makes it 0, this makes it 0, this makes it 0. That's 0, and then 2 is 0 here. Now, we have some rules. Second derivative rule is probably the most interesting in this case. When the first derivative is 0 and the second derivative is positive, you have a local min. When the first derivative is 0 and you have the second derivative is negative, you have a max. So I'm going to use these 0 points at negative 2. I'm going to plug negative 2 into this derivative in here. If I plug negative 2 in, I get negative 120 times negative 2, which 2 negatives make up positive. Alright, then I'm going to put positive 2 into that same second derivative formula. 60 times 2 is positive 120. 2 minus 4 is negative, so this is negative. I'll tell you right now, this is a local max by the second derivative rule. This is a local min. And I can use those to find the values of the first derivative. Alright? And I find that it's positive here, then a local max, positive to negative. And again, I only have to worry about that. So then the first derivative rule. And you can check those if you want and plug them in. You're going to find them right here. Alright? That is what happens. Alright? So I can now tell you areas of increasing, decreasing, points of inflection, and concavity, all from that table. When the first derivative is negative, you have a decreasing function. So it's decreasing from negative infinity to negative 2, and from 2 to infinity. It's increasing from negative 2 to 0, and 0 to 2. It is not increasing or decreasing at 0 or at 2 or negative 2. Those are zeros. So that's one thing I'll ask for. The next thing I'd ask for would be concavity, which I'll do in red. It's concave up where the first derivative is, or when the second derivative is positive. I'm actually going to have to find 2 more regions I didn't notice here. I'm going to have to do those 2 regions. So when I put in negative 1 into the second derivative, I get negative, and here I get positive. So it's concave up from negative infinity to negative square root of 2, and from 0 to positive square root of 2. And it's concave down from negative square root of 2 to 0, and from square root of 2 to infinity. And now I really have enough information to graph this thing. And finally, points of inflection happen at sign changes. So here's a point of inflection, goes positive, negative, negative, positive, and positive, negative. So there are 3 points of inflection. There are PIs at x equals negative square root of 2, 0, and square root of 2, 3 points of inflection. I didn't figure out the y value, but there were 3 sign changes, and it happened to be where the second derivative was negative all 3 times. So those are points of inflection. I can now take all this information and make a graph of this function. So I know I have a local max and a local min, so I'm going to go dual page and try to graph this out. Adding a new page here. So one, 2, negative 1, negative 2, and I'm going to put square root of 2 here, a little mark for square root, which is about 1.5 on each side. And I don't know what the max or mins are. The scale on the y is going to be something different because I'm not going to calculate them. So I sit here and I know, using green for the first derivative, that's decreasing to negative 2, and it's a local min at negative 2. So it's decreasing, and it has some sort of local min right down here at negative 2. And I don't know if that curve's going to have to go up or down. I could put negative 2 into the original function and figure it out. If it's a local min, my guess is it would be well below the x-axis. So maybe we just put it down here. We'll do this. And it's concave down until square root of negative 2, or concave up, and then it goes concave down. So there's a concave up to square root of 2. Now it's concave. Oh, and it goes through 0, 0, so I can move this all down some more. It's going to go through 0, 0, so I'm going to have to make my graph a little bit better than this. I did figure out it went through 0, 0. And it's going to come through 0, 0. And this is not the world's greatest picture. It's concave down right now. After this point, it goes from concave up to concave down. So I can get rid of that, and there's our concavity. And again, this takes some. This is why you do things in pencil. And then at square root of 2 goes from down back to up. And this is not an exact figure, but it's going to be something like this. And if I wanted to know exact values, I could figure out so I'll back up. I made a mistake here. I made a mistake on the increase and decreasing. This is not right. I was checking my values. It has a local max here. So it's increasing to decreasing. It has a local min over here. Decreasing and increasing. It goes through 0, 0. It has a concavity. It's that's a little better. Again, it's not a great curve, but through 0, it stays increasing, but you notice the concavity changes from concave down, concave up. All right. So again, I might have to resketch this if I was doing this for a test. It's easier said than done. I wouldn't have one this hard tomorrow. There we go. And that would be our function. So again, finding the points, making a rough sketch of the curve, having the concavity right. And again, sketching the curve is only going to be 5 points out of possible 75. So 70 points is on the left side, 5 points is on the graph of function. Braxton, midterm's coming.